Welcome back, everyone. First and foremost, give me a thumbs up if I'm audible and visible. No issues in voice and video. Fine, great, wonderful. All right. So, we are in the last chapter of the day, and this is nanotechnology. Now, first and foremost, from the perspective of your examination, from prelims and mains perspective, I would say that this is a chapter which is more important for your prelims examination than the mains. But it is not that the questions from here do not come in the mains examination. Questions can come in the mains examination as well. And this is what we have seen, that there are questions in the past which have come related to the mains examination also, in the mains examination also, from nanotechnology. In last 10 years combined, there have been like three questions in the mains exam, two questions in the mains examination from nanotechnology, but pre- uh, uh, largely in the prelims examination, we see that more or less they keep on asking questions almost every year from nanotechnology. So this is going to be the last chapter for us. We probably will be able to uh, end the session probably by 7:30 today, because I think this chapter will be done in the next almost 2 hours. So let's begin. So first and foremost, let's try to understand what do we mean by nanotechnology. What is the meaning of nanotechnology? So there are two words that you see here, right? Nano and technology. So nano, basically, when do you use the word nano? We discussed about nano satellites, correct? So why did we say nano satellites? Because these were satellites which were small, that had very less mass. That's why we called it as nano satellites. Similarly, what we see is that in cases of anything that is small, we tend to call it as nano. When Tata launched its small compact car, it named it as Tata Nano. So that's why when we say nano, we basically mean something that is very small, and that's why it is actually derived from a Latin word nano, which actually means dwarf. So the dictionary meaning from the word that is derived from Latin is dwarf, and that's why something that is very small, in that context we often use the term nano. But when it comes to the scale, we talk about nano because it is in the scale of 1 nanometer. And how much is 1 nanometer? How much is 1 nanometer? I was just about to write the answer. How much is 1 nanometer? Yes, 10 to the power of minus 9 meters. 1 nanometer is equal to 10 to the power of minus 9 meters. So here we are talking about the scale of 10 to the power of 9 nanometers, which has been named as nano scale. Now, how how special is this scale? 10 to the power of 9 meters. How special is the scale that the entire branch of science has been named after this 1 nanometer scale? There's no micro technology, there is no mini technology, there is only nanotechnology. So why is this particular scale 10 to the power of 9 minus 9 meters so special? So understand this first. So let's try to figure out why nanotechnology. What is so special about this particular scale that we named the entire branch of science uh, after this particular scale? Now, when you look at matter, everything that you have around you, you know that all these matter, you might have studied that they are made of molecules. Matter is made of molecules. Molecules are made of atoms. Inside the atoms, we had discussed that you have protons, electrons, and neutrons, and so on. Now, at the level of the subatomic particles, so you have the subatomic particles, correct? You have the subatomic particles, which are protons, neutrons, and electrons. Now, at the scale of protons, neutrons, and electrons, the subatomic particles are not different, meaning that even if you have a proton in oxygen, proton of oxygen is not different from proton of carbon. There is no difference there. So electrons, protons, and neutrons, wherever they are, in whatever element they are all the same. They are all having the exact same property, and these subatomic particles, they arrange in certain way to form an atom, and groups of atom form a molecule. Now, molecule is the first instance where any given material can have its independent existence. Because in terms of even an atom, an independent existence is not possible. All right. Independent existence is not possible. They would always exist in bunch of atoms forming a molecule. And this scale, when you form a molecule, this is the scale that becomes very special, because all the properties of any given element, or sorry, even any given molecule or any given matter, actually start showing up for the first time at this particular scale of a molecule. And this molecular scale basically is the nanoscale. About 1 nanometer, sometimes 0.1 nanometers, sometimes 10 nanometers, sometimes 100 nanometers. This is the scale. Sorry, this is the scale where you have all these molecules for the first time, and hence all these properties the molecules show, they start to appear for the first time in at this particular scale of 1 nanometers. So that is why this becomes very special, because at an atom level, it's not possible for that element to have its independent existence, right? At subatomic level, everything is similar, there's no difference. So that's why molecular scale becomes very important, and this is for the first time that we see that all these properties start showing. Let me give you an example. Suppose we take hydrogen and oxygen. All right, so we have the atom of hydrogen and atom of oxygen. These two can combine in two ways. Either they can make H2O, or they can make H2O2. What is H2O2? H2O, I'm sure you know. I'll not ask you what is H2O. What is H2O2? Hydrogen peroxide, right? So it is hydrogen peroxide. Now this hydrogen peroxide, the properties that hydrogen peroxide has is very different from the properties of water. That hydrogen peroxide can be used as an oxidizing agent, it can be used as an antiseptic, it is used as an industrial chemical in many of the things. As a catalyst, it can be used in certain cases. So it has antimicrobial properties. So there are various different properties that we have, uh, that are there in hydrogen peroxide. Yes, Glum, you're correct. For washing also we can use it. So there are various different ways in which hydrogen peroxide can be used. And then I need not tell you what water is used for, but the properties are very different. They are completely different. I mean, for example, you can drink water, you can't even think of drinking hydrogen peroxide. Please don't do that. So that's why we see that in these two cases, what is the difference? The difference is only one extra oxygen, and just one extra oxygen is completely changing the way these two chemicals behave, or let's say these two compounds behave. Correct? So just one extra oxygen and the entire world changes. So this is basically what we see in terms of any compound formation. And forget about the fact that, okay, here you can say that fine, oxygen and hydrogen are combining and fine, something can happen. Let's say if we consider carbon. Now carbon, we know, can exist as diamond. The same carbon can exist as graphite. And we discussed about coal as well, that coal is also nothing but carbon plus some impurities. So overall what we see is that the same carbon can be diamond, the same carbon can be graphite, and same carbon can be coal. So here you don't even have any extra element, it's just carbon and its arrangement. That the arrangement of carbon changes, and with just the arrangement of carbon atoms among themselves changing, one is diamond, one of the most precious stones that we have on the earth, and on the other hand graphite that you use in your pencils, and then third is a fuel. Completely different properties, right? So all these three forms, they have completely different properties. The only difference is the structure of carbon, the arrangement of carbon atoms, the connections of carbon atoms among themselves. So that brings in all the differences. So that is something that is very unique, and this all happens where? Nanoscale. This all the changes, all the properties, they start showing up where? At the nanoscale. So that's why this nanoscale becomes such an important scale, and that's why the entire technology has been named as nanotechnology, right? So that's why nanotechnology, and nanotechnology becomes very, very crucial, because now even if you want to manipulate the properties of any element, all right, let's say you want to manipulate the properties of any element, or let's say any material, then that also will happen here. Let me give you another example. All right, let me give you another example. Suppose that you have two surfaces. All right, there is one surface like this, and there is one surface like this. Let me call it as A, let me call this as B. And suppose that heat is being supplied to both. Heat is being supplied to both. Now, if I ask you, among A and B, which will melt first? Whether I'm launching the poll also for you. Just think whether A will melt first or B will melt first. Mark your answers. Whether you think that A will melt first or you think that B will melt first. All right, so it's almost equal, that 45% of you feel that A will melt first and 55% of you feel that B will melt first. All right. Can you tell me the reason? Why did you think A or why did you think B? In the chat, can you give me the reason? Why A or why B? B has larger surface area, less surface area. So, I mean, the answers are correct, but which has less surface area? A. So, which will melt first? A. So, B will not melt first. A will melt first. So, basically, what will happen is that all the heat that you're supplying to B is concentrated at this point, right? All the all the heat that we are supplying to A is concentrated at one single point. Whereas when it comes to B, first the heat will start getting distributed. All right. First the heat will start getting distributed all throughout the surface, and then on further heating, we'll see that it will start perhaps melting. So that's why, because the surface area is larger in B, it will take more time to absorb all that heat and start melting. Whereas in case of A, all the heat will be concentrated at one single point in this A, and hence it will melt first. Right. So that's why between A and B, A will melt first, not B. Now, if let's say, now the next thing I'll tell you, why did I even ask you this question? If I have to produce a material, if I have to produce a surface, a material with high melting point. So if I have to increase the melting point, what do we do? How do I manipulate the surface so that I can increase the melting point of the given substance? I can flatten out the surface, correct? At the molecular level, if I can flatten out the surface, it will of course take a lot more time to gain that heat, absorb that heat, and hence I'll be able to increase its melting point. So this is the beauty and the possibilities and the future of nanotechnology. That nanotechnology becomes a very, very crucial aspect of our technological future, because there are a lot of things where we right now theoretically see that it could be possible, and nanotechnology will make it possible in the coming days. And we'll see that there are a lot of instances, there will be a lot of cases where nanotechnology will start playing a very, very important role. All right, it already has started playing an important role, but the kind of growth that is expected out of nanotechnology is, I would say, still to happen. That's still early days, although it has been almost like 30-40 years since the time we started researching on nanotechnology a lot. But still, I would say that these are early days for nanotechnology, and there is a lot more scope that nanotechnology has, and that is what we'll see in the future. So that's why we see that entire properties of materials can be changed. That if I can do this, I am just trying to now look for the different types of manipulations that I can do. How can I change the color? How can I change the properties? How can I change any physical or chemical property of any given substance? Possibly everything can be done with the help of nanotechnology. So that is the beauty of nanotechnology, and why nanotechnology becomes such an important uh, piece of science for the future. So anyway, so coming to nanotechnology, the term, it comes from the Latin word for dwarf, and here we are talking about, refers to nanometer. We are talking about 1 nanometer scale. Now, when it comes to this particular scale, what we understand is that nanotechnology, when we are defining nanotechnology, it is the branch of science that deals with minute particles in the range of 1 to 100 nanometers in size. All right. So generally speaking, we are talking about 1 to 100, sorry, 1 to 100 nanometers in size, but it's not a rule. Even the materials that are 0.1 nanometers in size, or little less than 1 nanometer in size, even they will be considered as a part of nanotechnology. So overall, everything in and around the scale of 1 nanometer, it will be considered as nanotechnology. So if you look at all these substances, you'll see that this part right here, it can be, all these can be called as nanomaterials. They all can be called as nanomaterials because they are in this perfect range. And in comparison to them, if you look at the others that you have here, for example, you have the virus, which is almost 1000 times bigger than a nanomaterial. Same goes for the red blood cells as well. Hair is much bigger, and then after that we come to the so here on we come to the things that we can actually see. So that's why nanoscale is much smaller than all these, and this is where the molecular formation for the first time begins, and all the properties in any given material, they start to show for the first time at this particular scale. Now, looking at our understanding of nanotechnology compared to whatever we have discussed until now, space technology, nuclear technology, biotechnology, all these have been here for quite some time. Space technology, anyway, for perhaps more than 1000 years, that we have been doing some kind of space observations and research. In case of nuclear technology, also, at least for the last 100-150 years, there is an immense amount of research that has happened in the field. Biotechnology, also, more than 70-80 odd years, there is enough research that has happened in the field. But compared to that, when we look at nanotechnology, it's a far newer science and a very complex technology. The name nanotechnology itself did not exist until 1974. And all of the origin, all of these stories, it begins, you can see, in a manner in 1959. In 1959, there was this lecture that was being delivered by the great American physicist Richard Feynman. And Richard Feynman, while he was delivering the lecture, he said something that became very popular. He said, "There's plenty of room at the bottom." So he said, "There's plenty of room at the bottom." Now, when he said plenty of room at the bottom, what he basically meant is that all the research that we do right now, and this is 1959, all the research that we do right now, it's more confined to what we can actually see, what's there in front of us. We have never tried to go beyond what we can actually see, go to the atomic or the molecular level and see the world there, understand the world that you have there. If we go there, we perhaps will find a completely new world that we have never even imagined. And this is correct. We saw that being established with quantum mechanics as well. So we'll discuss about those things later. But in a manner, the speech that he had delivered in 1959, it became the base for all the research and all the studies to happen in the coming days and coming years. Because Richard Feynman was a very famous scientist. All right. He was very famous. He was very popular among the students and the scientific community at large, and they used to worship him, they used to follow him with whatever he would say. And that's why, I mean, even the biography that was published, there's a wonderful book on his biography, Surely You Are Joking, Mr. Finman. So Surely You Are Joking, Mr. Finman became one of the best sellers in the world. So a scientist's biography becoming one of the best sellers in the world is quite unheard of. But this did happen in case of Richard Feynman, that his biography became one of the most hot selling books because of the stories that you have, because of the legendary stories that we have from his life. That, for example, when he was just 10 years old or 11 years old, This is when he was listening to his radio, as all of our mothers do. His mother also did not let him listen to the radio and asked her to do something and go and study. So when the radio was taken away from him, he made his own radio. He was just 10 or 11 years old. He was able to make his own radio just sitting in his room. So that just shows the genius of the person, and he was one of those people who has contributed immensely to the atomic research, the quantum research in the US. So that's why when he said plenty of room at the bottom, many of the scientists and students alike, they started following him. They started taking this thing seriously, and we see that now the developments in this field start. Then we see that there was a formal name that was given to this branch, nanotechnology, and this name was given by a Japanese professor, Norio Taniguchi. So Norio Taniguchi was the person who gave this name officially, nanotechnology. So you can say that in a manner now it became a very well-defined branch of science, nanotechnology. But yet all the research that we were doing until now was theoretical, because we did not have any instrument that could look at the level of nanoscale. We had microscopes, but these microscopes did not have the capacity of going beyond, let's say, 10 to the power of 5, or maybe 10 to the power of 6 meters, 1 micrometers, and so on. Beyond that, they did not have the capacity, because most of these microscopes were optical microscopes using the visible light. And nanoscale is beyond the scale of visible light, so you cannot see it with visible light. So it's just like, let's say you have a smaller hole and the light particle is bigger. So light particle cannot actually enter inside it, so you cannot see anything inside it. So that's why at the nanoscale, you cannot really see anything. You cannot see what's inside this nano particle, because the visible light particle itself is actually bigger than the nanoparticle. So that's why most of the microscopes that we had, they were optical microscopes. So that's why they did not have that capacity. So overall, all the research that we were doing, all the studies that we were doing, it was still theoretical, right? It was still theoretical in nature. That changes in 1981 when scanning tunneling microscope is invented. 1981, we see that scanning tunneling microscope gets invented, and with the invention of scanning tunneling microscope, now we have the capacity that we can go beyond the microscopic level, and even nano materials can be seen with the help of scanning tunneling microscope. So that's why it was a big breakthrough in the field of nanotechnology. And of course, because of this, even Nobel Prize was given to the scientists who had invented scanning tunneling microscope. Now, when it comes to scanning tunneling microscope, understand the basic functionality of how it functions. There are two basic principles on which this works. One is the quantum mechanical effect of something called as tunneling. And then after that, there is another effect, another concept called as piezoelectric effect. So these two are the basic concepts that help scanning tunneling microscope see at the see at the nanoscale. Uh, uh, so understand what is happening here. Look at this particular picture. So what happens is that there will be a metal tip, and this metal tip will be incident on the surface of the material. And while it is incident on the surface of the material, it applies some pressure here. All right, it applies some pressure on the material, and when it applies this pressure, because of this pressure, we see that there are some electrons that are emitted. There are some electrons that are emitted, and this phenomena itself is called as piezoelectric effect. So that's why piezoelectric effect basically is the electricity produced by applying mechanical stress or pressure. All right, mechanical stress or pressure. So if so happens that when you are applying pressure on something, if electricity is produced because of that, then in that case you can say that this is piezoelectric effect. All right. So that is what happens in case of piezoelectric effect, that when mechanical pressure is applied, it will produce electricity. So piezoelectric effect. So now what happens is that this metal tip, when it touches the surface, applies pressure on it, electrons are released. Now these electrons that are getting released here, they can enter inside the surface. They'll be able to make a tunnel through the surface. All right. So what happens is that, let's say that we have the surface like this. All right. If we have the surface like this, then what we see is that the electrons, they will be able to enter inside the surface. Right. They will be able to enter inside the surface, basically making a tunnel through the surface. So that is why this other phenomena is called as tunneling. All right. That is why the other phenomena is called as tunneling. So when it comes to tunneling, that what tunneling means is that electrons are able to break the energy barrier and enter the surface, enter the surface, making a tunnel for itself. So this is what happens in this particular case, and this is called as tunneling. All right, this is called as tunneling. So these two quantum mechanical effects, one being tunneling and then another one called as piezoelectric effect, these two together are able to probe through the surface and analyze the surface and give you an output about what the structure of the surface is like and what is exactly this surface made of. You will be able to get this. So that's why scanning tunneling microscope, in a manner you can say, it changed the landscape of the researches that were happening until now in nanotechnology. It completely changed nanotechnology forever, because now it was very exciting for the scientific community that now we at least have an instrument which will enable us to see what's there inside the surface. Until now it was a very theoretical aspect. So what we see is that scanning tunneling microscope was invented. Then later on there is another microscope called as atomic force microscope. So atomic force microscope also was invented, and in this case also, more or less you'll see that it works in a very similar way, where this also will have a sharp tip which will be mounted on the surface, and as it moves across the surface it is able to map the surface. All right. So instead of directly applying mechanical pressure, now it will keep on moving across the surface and try to map the surface that it is incident on. So this is basically what we see in this particular scenario. Now overall, when it comes to uh, scanning tunneling microscope, there is a limitation that scanning tunneling microscope has. We are talking about producing electricity and electrons entering the surface. That can also be that can only be possible when you have conducting surfaces. So scanning tunneling microscope will only be useful if you are using it for a conducting nano surface. So if it is a non-conducting, let's say a non-metallic surface, then scanning tunneling microscope doesn't work. Then in that case, that's why atomic force microscope was a requirement, and it filled the gap that was there in the research because of scanning tunneling microscope. All right. So that's why this is something that we see over the surface. So overall, so that's why as the tip moves across the surface, it interacts with the sample's atoms and generates a three-dimensional map of the surface, which can be used to determine the sample's roughness, texture, and other surface properties. So overall, where uh, atomic force microscope becomes useful, it fills the gap with respect to a limitation that scanning tunneling microscope has, that it can be used only to see the conducting surfaces. All right, so this is what we see with the second microscope. So now that we had these two microscopes, we now had the ability that we can see all the nanoparticles. All right, metals or non-metals, we could see the nanoparticles. Then there was a discovery, and this was the discovery of fullerenes in 1985. In 1985, we discovered the first nanoparticle, first naturally occurring nanoparticle, and this was fullerenes. Now, the structure of fullerene looks something like this. As you can see that it's a football-like structure, correct? It's a football-like structure where you have all these carbon atoms, where we have all these carbon atoms, right? So all these ball-like structures, these are carbon atoms, and all these rod-like structures, these are the bonds between carbon atoms. So you'll see that most of this, the arrangement is in a hexagonal form, and this hexagonal form takes a spherical shape. So this was the fullerene that we had discovered, and this spherical fullerene especially has been named as Buckminster fullerene. Buckminster fullerene, also sometimes called as buckyballs. So this basically was discovered. Now with this discovery, when we were analyzing this particle, we also saw that the properties of this particle were wonderful. That it had very good electrical properties, very good uh, uh, thermal properties, optical properties, radical scavenging could be done. We'll discuss about that later. So all these things actually were present in this one particle that we discovered. So that generated all the more excitement, that this is just the first nanoparticle that we have discovered. We don't know what is in store, and this was all again made of carbon. It was all again made of carbon and nothing else. This was more or less, you can say, carbon 60. So we basically found a new particle, and this was the first such particle, so generated a lot of interest that there could be so many more such particles that perhaps we have not seen yet, and that led to more discoveries. The next synthesis that we did was of a carbon nanotube. Now if you look closely, again you see the same thing, that you have the hexagonal structures, but this time arranged like a cylinder, this time arranged like a tube, correct, in a cylindrical form, and that's why this was named as carbon nanotube. Now even for carbon nanotube, another Nobel Prize was given. Now this you will see that the last 20 odd years, last 20-25 odd years have been the era of nanotechnology, because every time you do something new, get the Nobel Prize. Any new discovery, get the Nobel Prize. Any new invention, get the Nobel Prize. And this often happens with anything that is new. So for example, 100 years back, nuclear technology was new, and that's why at that point of time you will see that a lot of Nobel Prizes kept flowing towards nuclear technology. So and forget about scientists getting it, it was running in the families. That for example, Madame Curie, famously known for her discoveries or her studies related to radioactivity, she got the Nobel Prize. Later on, her daughter also got a Nobel Prize. So within a family itself, people were just getting Nobel Prizes back then. And same again started, also started repeating with nanotechnology, and still keeps on happening, that people are getting new Nobel Prizes on nanotechnology all the time. So that's why there are all these aspects that we see, and nanotechnology, because it's such a new science, new discoveries and inventions keep on happening. So with carbon nanotubes, again we saw wonderful properties. If you look at the set of these properties, for example, high thermal and electrical conductivity. good optical properties, flexibility, increased stiffness, high tensile strength, lightweight, ability to be manipulated yet remaining strong. So in all these cases, these are the properties that make carbon nanotubes so special. Because of this only, we can say that carbon nanotubes are very, very special, because they can actually perform a lot of functions for us. And therefore, when we start looking at the various application areas, we'll find that there are n number of application areas where we can perhaps use them. So if you look at some of these examples where we can make the use of carbon nanotubes, first, in electronics. In electronics, what we see is that they can be used to create highly conductive wires, transistors, and other electronic equipments. So now, overall, what we have seen is electronics is one core segment where nanotechnology has done a lot, and even carbon nanotubes, being a nanomaterial, has actually done a lot to provide those kind of electrical conductivity with very thin surfaces and strong surfaces at the same time. All these things have been made possible in electronics because of carbon nanotubes. So that's why carbon nanotubes have played a big role in electronics and the development of electronics that has happened over the course of last decade or so. Then, in case of energy, now overall what happens is that carbon nanotubes, they have very high surface area. So because of the high surface area, the surface available for electrical conductivity is also higher, meaning that they would become very, very good as anything that requires to store energy. So that's why we can use it in making solar cells. We can make it in use it in making lithium ion cells, fuel cells, etc. So in all these cases, we can use it mainly because, as I told you, that they have high surface area, high electrical conductivity, and that's why they can increase the efficiency. They can increase the efficiency of the energy storage and conversion of the devices. So that's why we see that in all these cases, it can become very, very useful from the perspective of energy applications as well. Then in biomedical applications also, we can make the use of carbon nanotubes. Now what we see is that there are imaging applications, imaging devices where we can make the use of carbon nanotubes. But most importantly, carbon nanotubes are used or can be used in drug delivery mechanisms. Now, how exactly drug delivery mechanism? If we want a targeted delivery of drug to a certain part of the body, then carbon nanotubes become very useful, because carbon nanotubes would have a size of what, like let's say 1 nanometers, correct? Blood vessels, or let's say a red blood cell which keeps on traveling all across the body, what is the size? Almost 5 micrometers. So in a manner, you can say that a blood cell is almost 1000 times bigger as compared to a carbon nanotube. So that's why carbon nanotube can very easily enter inside the bloodstream and travel inside the bloodstream. So that's why it can become even a carrier of the drug. You can make a drug carrier with the help of carbon nanotubes to make drug delivery possible. And this is also one aspect for which a Nobel Prize already has been given, the 2016 Nobel Prize. The 2016 Nobel Prize in Chemistry was given for making molecular machines. Molecular machine. So these molecular machines are nothing but these nanoparticles which can act as a carrier for drug delivery. So even this is a very important aspect. Then in making composite material, the composite material, mainly because the strength that carbon nanotubes have, or the thermal properties that the carbon nanotubes have, they can be used to strengthen the properties of different materials. They can be used to strengthen the properties in a manner that we'll see that overall they will increase the strength and even electrical conductivity for that matter. So that's why they can be added to polymers, metals, and ceramics to create strong, lightweight, and heat resistant material. Then apart from that, there are environmental applications as well. For example, we can again, because of the high surface area that we have, we can make the use of carbon nanotubes to make filtration membranes for water filtration. And even in air filtration also, we see that sensors can be created so that pollution detection can be done. So that's why environmental applications, and then there can be aerospace applications as well, because it is lightweight, it is very strong. So that's why it can be used. Because of these properties of the material, we can replace the metals or everything else that we use in the aerospace industry, or even in case of the space or space technology also. Our uh, space the launch vehicles also, they can also make the use of carbon nanotubes. So that's why there are multiple such applications. When we look at the future, we also understand that there are multiple different ways in which in the future also carbon nanotubes are going to have a big role to play. And that's why we are still in an active research mode. We still are in an active research mode. We still see that there is so much of scope, and there are so many things that can be done by carbon nanotubes. And slowly and steadily we are breaking the barriers, we are going into these fields, and we are creating new opportunities for carbon nanotubes as we see. Look at this question. This was an interesting question asked in your 2020 paper. Read the question. Meanwhile, I'll launch the poll for you as well. All right. So what I see is that 7% of you have marked A, 27% of you have marked C, and 67% of you have marked D. So let me discuss this question with you. With reference to carbon nanotubes, consider the following statements. First statement is they can be used as carriers of drugs and antigens in the human body. This is perfectly fine. Correct? This is perfectly fine. We discussed about this, that they can be used as carriers. So yes, one is 100% correct. Second statement is they can be made into artificial blood capillaries for an injured part of human body. So what we are saying is that for an injured part of human body, we would make artificial blood capillaries with the help of carbon nanotubes. Now, there is this branch of science which is called as tissue engineering, where even genetics is being used, or even nanotechnology is being used. In tissue engineering, what we basically try is that any injured part of the human body, we try to make artificial cells, we try to make artificial tissues or organs which can actually help the person move on with their lives. Even in case of burn victims also, we see that tissue engineering works. So, as a part of tissue engineering, it is an active field of research where we are even looking for making these blood capillaries as well with the help of carbon nanotubes. So the question says they can be made. So generally speaking, can be should not be wrong. All right. So let's hold on to this statement for now. Third statement is they can be used in biochemical sensors. This is correct. They already are being used in biochemical sensors that many have made. Even NASA, for example, has used it in many of their projects. So three definitely correct. And then the fourth statement, carbon nanotubes are biodegradable. Now, this is a statement that personally speaking, I don't believe that this is correct, because carbon nanotubes are very uh, solid structures, very stable structures, and it's not very easy to destroy carbon nanotubes. All right. So decomposition of carbon nanotubes is very, very difficult process, and you cannot simply uh, uh, say that a microorganism will be able to just eat up carbon nanotubes, it will take a lot of time. It would take thousands of years before a microorganism will be able to destroy the surface of carbon nanotubes. So generally speaking, when it comes to the disposal of carbon nanotube made based material, we use the process of incineration. Incineration meaning that we heat it up at very high temperature, almost we take it up to 800 degrees Celsius to destroy the structures of carbon nanotubes. So from this perspective, if you are asking me my personal opinion, I would say that this is wrong. And I would say, I'm saying this is my personal opinion. I would say that two is correct because of the word can be, that you cannot rule out the possibility. If let's say it is an active area of research, maybe in the future, maybe perhaps in next 10 years or maybe 50 or 100 years, you cannot say that it cannot happen. Now, official answer was this. Official UPSC answer. Official UPSC answer was C. If you ask me, I'm writing here also so that it doesn't create controversy, my personal opinion. My personal opinion, answer should have been 1, 2, and 3. The answer should have been 1, 2, and 3 and not 1, 3, and 4. But this is the official answer, so we can't do anything about it. But I don't know on what basis they think that 4 is correct and 2 is wrong. I wouldn't really agree with that. I also read a lot of research papers also after they gave this official answer. I'm still not sure why they are considering 4 as correct. Because if you consider that there are certain research that is going on where we talk about certain microorganisms which can be used or which can be genetically modified so that they can act on carbon nanotubes. But then that is a completely artificial process and you cannot say that they are biodegradable. Then in that case, we can even say that plastic is biodegradable, because we are working uh, on these kind of projects and research as well, where we want to introduce certain microorganisms that can act on plastics as well and degrade the plastics. So from that perspective, if you apply that logic to plastic, you can apply the same logic to carbon nanotubes. So that's why I really don't believe that 4 should have been correct. But this is the official answer that was given, 1, 3, and 4. Moving on to the next nanomaterial, which is nanowires. Now, in case of nanowires, these are very small. That's why nanowires, the diameter is up to 1 nanometers. Now, in case of nanowires, they also show remarkable optical, electronic, and magnetic properties. So that's why they will be very useful in storage, data storage, and in general, when it comes to electronics, electronic devices, building tiny chips for computers. In all these cases, nanowires will be useful. They will be useful in shrinking the size of the electronics, and efficiency could be increased with the help of nanowires. So that's when nanowires can become useful there. Then after this, there is this one very, very important material which is called as graphene. Now, when it comes to graphene, again, if you see, you would see the same structure, that it also has a hexagonal structure, right? This also has hexagonal arrangement of carbon atoms, but this time instead of a sphere or a cylinder, this time it's a sheet, right? It's a two-dimensional sheet, and again, a hexagonal arrangement. Now, with graphene, the things are uh, very exceptional. Now, with when it comes to graphene, the same stacks of graphene, when they are stacked one over the other, the same graphene will form graphite. So graphite is nothing but stacks of graphene laid one over the other. That will become graphite. Now, when it comes to graphene, we see that it is two-dimensional. With graphene, we have seen that it has wonderful properties. If you look at the properties that we have, one of the best conductors of electricity, one of the best conductors of heat at new room temperature, strongest natural compound discovered, thinnest compound known with just one atom thickness. So in all these cases, we see that there are so many great properties that graphene has in itself, and because of this it was also named as miracle material. The discovery of graphene basically was named as miracle material. And now this discovery of graphene is also very special, and this meme basically signifies that this is a very special case that we saw. The scientist who who eventually also got the Nobel Prize for the discovery of graphene, they were just playing around with sellotapes. Sellotape, the sticky tapes. So they basically had taken graphite, and they were just uh, sticking these sticky tapes on the surface of graphite and just peeling them off. So while they kept on peeling them off one by one, while playing with, you can say, the sticky tape, they discovered that graphite was made of graphene, and discovery of graphene happened like this. So it was not a very complex procedure or very advanced scientific invention, or sorry, discovery, but just two scientists playing around with sellotapes. So I mean, sounds very funny and non-serious, but that was actually not the case. But yes, they actually were doing this experiment, and while experimentally, they stumbled upon graphene and got the Nobel Prize for it. Yes, so playing around with tape gets the Nobel Prize. So this is what happened, and with graphene, with the discovery of graphene, with all the properties that we see with graphene, we thought that the world is going to change forever. We just thought that the world is going to change forever, because look at these properties. These are extremely great properties to have in one single material, because some of these properties would be there in, let's say, metals. Some of these properties would be properties of non-metals, some this metal, some that metal, some that element, from some this element, and all these great properties all in this one particular substance. So that's why discovery of graphene was great, and we thought that graphene is just going to change the world forever. But that didn't happen, right? That didn't happen. That although we saw that there are multiple ways we probably would change the world forever, but that has not happened. That still 20 years later, because 2004 the discovery happened, almost 20 years later now, we still see that there are only some pockets of applications where graphene is actually being used today. So for example, to enhance the strength of material, for LED lighting, then in electronic devices, in batteries and supercapacitors, then in water diffusion, and then water purification. So these are not the properties that we would think after a miracle material has been discovered. What happened to graphene? There are a couple of things that we realized about graphene. That first of all, synthesis of graphene would not be that easy, because you need a lot of graphite from where you have to extract graphene, and this becomes a expensive procedure altogether. All right, so expense becomes one factor. The second factor also is the usability. That yes, we understand that graphene is great with all its properties, but wherever you want to use, for example, let's say you say that okay, fine, it has wonderful electrical properties, then why not use it as electrical wires? Why are we using copper or aluminium wires? Why not use graphene? So first and foremost, graphene is going to be very costly. So you cannot simply just draw it into wires and start using graphene. It is going to be very extremely costly, which is not cost effective for your electricity supply. That is one thing. Second thing is that these copper and aluminium wires, given the circumstances, they are doing a good job. So when they are doing a good job, why to replace them? If they, let's say, if they were not able to function, if they were not doing good job, then maybe replace them. But when they are doing a good job on themselves, then what's the point of replacing it? So because of that, we saw that a lot of things that we imagined about graphene, that this is where graphene will change the world, that is where graphene will change the world, didn't really happen. So that's why we still see that there are limited number of use cases where graphene is being used. Today we see that in mobile phone devices, for example, in foldable devices, we are seeing that graphene is being used. But wherever you are using graphene, that also makes that particular instrument or device also very costly. That foldable display phones today are very costly wherever graphene is being used. There are OLED screens that you have, and there also graphene sometimes is being used, and they are also very costly. So that's why wherever we are using or using graphene commercially, we find that graphene is very costly there. So that is where the problem lies with graphene. Look at this question. This was asked in your 2011 paper. 2010, the Nobel Prize for graphene was given, and 2011 this question had come. So more or less, you can say that this was a current affairs question. So please read your statements. Meanwhile, I'll also launch the poll for you. Please read your question and mark the answers. Meanwhile, I'll just be back. I just have to go and drink water. All right. So, as I see, oh, great. 67% of you have given the correct answer, which is C. So, graphene in the news frequently, was it, what is its important? First, it is a two-dimensional material and has good electrical conductivity. This is correct. We discussed about this, that it is a two-dimensional sheet and one of the best conductors of electricity that we have ever discovered. One of the thinnest but strongest material tested so far. This is also correct. Entirely made of silicon and has high optical transparency. Not made of silicon, made of carbon. So that's why 3 is wrong. Can be used as conducting electrodes required for touchscreen LCDs and organic OLEDs. So we just discussed that in OLEDs, etc. also we are using it. So the correct answer here will be C. Now, the next nanomaterial is quantum dots. Now, in case of quantum dots, we are saying that these are called as quantum dots mainly because, first and foremost, quantum mainly because they have quantum properties. They have the properties that the subatomic materials or subatomic particles have, and dot mainly because they are spherical in shape, very small in size, just nanometer in size, near about 1 nanometer in size. So that's why the name quantum dot has been given to them. So now in this particular scenario, what we see with quantum dots is that when ultraviolet light is passed through the quantum dots, they would emit various different colors. And these colors will be dependent on the size of the quantum dot. If it's a bigger sized quantum dot, we see that it would emit reddish color. And if it is small sized quantum dot, it might basically be blue or violet. So we see that this kind of a scenario will be seen depending on the size of the quantum dot. Now, this also is based on the wavelength because red has the biggest wavelength and blue or violet have the smaller wavelengths. So that's why when you have the bigger size quantum dot, then in that case you will have red color, and when you have smaller size quantum dots, you would have the blue or the violet or indigo color. So that is what we see with quantum dots, that they would basically start showing various different colors when ultraviolet light is passed through them, and these colors will be dependent on the size of the quantum dot. Now with quantum dots, what we basically see is that quantum dots also have various applications, that for example they can be used in photovoltaic devices, uh, m- uh, mainly meaning the energy devices wherever electricity is being produced, we can make the use of quantum dots there. Then they can also be used in LEDs, where we have something called as a QLED, quantum LED. So if you have seen the advertisements, especially Samsung advertises QLEDs a lot, because they have produced, they have put they have released their QLED TVs in the market, and there are other companies as well. But Samsung is the best known company for the QLEDs. So in QLEDs, when they advertise QLEDs, they say that QLEDs will give you better picture contrast compared to any other LED. That's the reason. That's the reason why, because these quantum LEDs basically are based on quantum dots, hence better picture or better contrast in picture will be displayed by them. Then in the medical field also they can be used. In the medical field also quantum dots are used. We see that especially, let's say, in the diagnosis and treatment of cancers, etc. Also we see that quantum dots are used there. And then photochemical conversion of water into hydrogen, it acts as a catalyst. All right, it acts as a catalyst when conversion of water into hydrogen through electrolysis is done. So that's why in this particular scenario also quantum dots can be useful. So overall, when we look at the different applications of nanotechnology, we understand that there are various different ways in which nanotechnology can be very, very useful. So for example, when we look at the various fields, let's say if we are looking at the medicine field, the health sector, then it can help in drug delivery. We discussed about the the carbon nanotubes. Even nano gold particles can be used, and carbon nanotubes can also be used in drug delivery. Then in case of tissue engineering, that question that we had discussed, it talked about tissue engineering, and there also carbon nanotubes can be very, very useful. Then in disease diagnostics also we see that nanotechnology will be very, very useful. And here also we see that some of the materials, like for example quantum dots, they can actually be used here. Even carbon nanotubes can also be used in such cases. Then nano carriers for eye surgeries, this also can be done with the help of certain metallic oxides, metallic oxide based material, we can do that. Then nano robots in surgery, because nano material, they are very, very small, so nano materials can be used for transfer of one thing to one, from one place to another. So in these cases we see that we would call them as nano robots. So it can be metallic oxide particles, it can be carbon nanotube particles. In these cases they all can be used. And then nano flares in breast cancer treatment, this is also where we see that quantum dots can be used. So that's why there are multiple different ways we see that different types of nanomaterial can be used in various different forms. Then in the energy sector, they can be used to address the shortage of fossil fuels. Shortage of fossil fuels. So here also we see that there are various different mechanisms, there are various different instruments that the world has been working on today, so that we would be able to bring out these kind of uh, material. So here also we see that carbon nanotubes can be used. Here we also see that nanowires can be very, very useful. Nanowires can be very, very useful. And at the same time, even in the photovoltaic devices, the quantum dots are also very useful. Then nano generators for wind energy production. Again, we see that in these kind of cases, carbon nanotubes can be very useful. Then nanotech solar cells, carbon nanotubes can be used. Quantum dots can be used. Even nanowires can be used. In all these things, they can actually be useful in making the solar cells. And even the other semiconductor nano devices, they also can be used there. Then quantum LEDs, we discussed that here we use quantum dots. Now, why in energy we are discussing QLEDs is because they have a good energy efficiency. The energy efficiency for them is high. Energy efficiency for them is very high. So that's why QLEDs are also being considered here. And then nano catalyst for hydrogen production, as we had discussed, that quantum dots can be used in such cases. Quantum dots can be used in such cases. So that also is a possibility for us. Then in the sector of food and agriculture, silver nanoparticles are used because they have antibacterial properties. Many other metallic oxides, all right, just remember this, that metal oxide, metal oxide nanoparticles are very useful in terms of food and agriculture. They are very useful in food and agriculture. So that's why we see that there are all these. So whether antibacterial properties, antimicrobial properties, we have titanium dioxide, which also has antimicrobial properties and also can be used in even sunscreens as well. So we see that there are various different nanoparticles, especially the metal oxide nanoparticles, that will be very useful in food and agriculture. Then we also have nano fertilizers, where I'm sure you might have heard about nano urea. So nano urea has been also in the news because ultimately what happens is that nano fertilizers, they have higher surface area, surface area, thus better absorption, better absorption into the soil, better absorption. So they can actually give you better productivity with smaller quantity. So that's why we see that nano fertilizers also can be very, very useful. Then in the environment also we see that for water purification we can use it. This is where graphene can be very, very useful. So we can make the use in graphene of graphene here. Then to reduce carbon dioxide also we can use purification methods where graphene can be used in these purifiers. Then even carbon nanotubes can be used in such cases. Then pollution control with the help of nano metal oxide nanocrystals, improving air quality and detection of pathogens. So in case of detection of pathogens also, graphene can actually be used as an indicator. So graphene we can use in these kind of cases. So in the environment also they have a very good positive impact. Similarly, when we are talking about electronics, in case of electronics also we'll see that they would have a very important impact, that in nano circuits with the help of nanowires, with the help of nanowires. Then in MRAMs, that is magnetic RAM, there also nanowires can be very, very useful because nanowires have very good optical properties. So that's why they can be very, very important storage devices. So hence we see that in all these cases we'll be able to make the use. Then use of carbon nanotubes. So carbon nanotubes, especially in electronics, or let's say wherever we are making to increase the strength of the electronic devices, or even in making the foldable displays, we can make their use. So the next point also talks about foldable displays. So we know that carbon nanotubes can be used here, and graphene can be very, very useful in making these displays. So we see that there are all these different ways in which we can make. So single electron transistors can be made with the help of nanowires. And to reduce energy consumption, we know that quantum dots are used. For example, when we discussed about the QLEDs, we know that they can reduce the energy consumption altogether. So then after that, in the industries, in aircraft manufacturing, in construction industries, in textiles, in even making COVID-19 masks, In all these cases also, we can make the use of various different nanoparticles. So aircraft manufacturing and construction industry especially, we see that carbon nanotubes are very, very useful in all these cases. Even in textiles, we see that carbon nanotubes can be used. In making COVID-19 masks also, there are various composite materials that can actually be used and have been used in making these kind of masks. And then in space, to reduce the spacecraft weight, this can be done with the help of carbon nanotubes. Similarly, to make elevators, this can be done with the help of carbon nanotubes. Now, this space elevator is a very unique concept. This is a concept where we are saying that we'll be able to go from the Earth to the space station with the help of an elevator. With the help of an elevator. And what basically NASA has been trying is that this wire of the eliminator, it would be made of carbon nanotubes. This is where carbon nanotubes will be very, very useful. Now, okay, so we are seeing that the elevators that we are using in our apartment buildings and offices, etc., they actually can be used to carry people and things from Earth to an Earth's to a space station. Very, very complex technology, of course, very complex technology. And NASA has been working on it almost for last like 25, 30 years, and still they haven't been able to. Even Japan, Japanese space agency, also has been working on it to make these space elevators. So very, very difficult concept because of everything that you have, every variable that you have. And I remember that for the first time, I might have read about space elevators when I was in class fifth or sixth, maybe. And then I remember that at that point of time, there was a science exhibition happening in our school. There was a competition, kind of competition, and where uh, I, along with my friend, we made the model of space elevator and went to the exhibition with space elevator model. And we explained everything, that whatever we had read in the newspaper and here and there, we actually went with everything and we explained it uh, uh, in in that exhibition. We got the first prize. We got the first prize because nobody understood what we were saying. Nobody had no Anybody had no idea about whatsoever what this space elevator was, which was very unique idea that we had just come across. We stumbled upon it in the newspaper and we just made a model out of whatever understanding that we had. Got the first prize because nobody understood what we were making. So space elevator as a concept has been in the making for quite some time now. Then solar cells to propel satellites and aircraft. So in making solar cells also, we understood that there are various different nanomaterials that can be used. So overall, we do understand that even in the space, it will have a lot of applications where it would be useful. Then in military or the defense applications as well. In intelligence gathering, for example, we can make the use of nanowires, because with the help of nanowires we'll be able to make very small electronic devices, hearing devices, spy devices that can never be easily tracked or intercepted. So that becomes a challenge. Then in making military vests also, carbon nanotubes can be used. It can be used to make stab proof or even bulletproof clothing, which will be very lightweight, so easy to carry for the people as well. And in wound care, where we discussed about tissue engineering, right? We discussed about tissue engineering. So in case of tissue engineering also, we see that this is something that can be useful. This is where also we can go and use this. So that's why there are so many applications. I mean, these are just some examples, I would say, of the amount of work that nanotechnology can do. And as I told you, that this is just the beginning of what nanotechnology is actually capable of. Look at this question. This was asked in your paper. Easy question, I would say. I'm launching the poll for you. Please mark your answers. Good to see. Almost 76% of you have given the correct answer. So let me read out the question. With reference to the use of nanotechnology in health sector, which of the following statements is or are correct? First statement is targeted drug delivery is made possible by nanotechnology. And the second statement is nanotechnology can largely contribute to gene therapy. So first, targeted drug delivery, we know for sure that this has been made possible. So we already are doing it, already are trying it. So one definitely correct. Nanotechnology can largely contribute to gene therapy. So can largely contribute, a very generalized statement is being made. Most of the times these kind of statements anyway are correct, but yes, this is correct because it will work in a very similar fashion as the drug delivery works. So similarly, we might be able to also make the use of nanotechnology in gene therapy. So yes, both these statements, statement number 1 and 2, both are correct. So correct answer will be C. Moving on, now we look at what India has been doing and what are the things that we have seen in India. Now, overall, when it comes to the Indian interventions in nanotechnology, as always, what has been the case in technology, we were a little late to arrive. All right. And initial years, when there was active research, extensive amount of research happening in the world, we did not really do a lot in the in the initial years, but slowly and steadily we started to pick up. But one special year was 2007. So until 2007, there were small interventions here and there. For example, the fifth 5-year plan. In the fifth 5-year plan, it promoted the research in nanomaterial. Then then after that, there was a program on nanomaterials, science and devices in the year 2000. So these were smaller interventions. But then after that, in the year 2007, we took something which is called as nano mission, popularly called as nano mission, a mission on nanoscience and technology. Now, this nano mission was taken in 2007 as a part of the 11th 5-year plan, that it will function for the next 5 years from 2007 to 12. But then we started seeing the success of this nano mission in the 11th 5-year plan, and then this was also extended to the 12th 5-year plan. All right. So initially, this nano mission was supposed to be taken for 5 years, but because of the movements and the successes that we started seeing in this nano mission, we also extended it as a part of the 12th 5-year plan. So this is a mission that ran for like 10 years. Now, this nano mission has been very, very crucial because until 2007, we were hardly doing anything. But with the help of this nano mission, we see that all the support was being provided to the nano research in India. And because of that, maybe one of the very strong reasons because of which we today see that India, when you look at the number of papers that have been published, one of the number of research publications in terms of nanotechnology, the highest number of research papers have been published by the US, second highest number China, and then the third highest number is India. So India right now, in terms of the number of papers, research papers that have been published in nanotechnology, India is at the third spot. So which is a great, you can say, a great learning for us, and because of that also shows the way we have been able to carry this nano mission, and the success of that nano mission translates into these kind of data. So what exactly was this nano mission? Let's try to understand this. So this is something that was taken as a mission, as an umbrella program for capacity building in nanotechnology. We overall were looking for better research, wider research in the field of nanotechnology, and find the potential, find the applications of nanotechnology that might be helpful for India, that might be helpful for India's development. So that's why this was the primary objective. And with the primary, I mean, primary aim, you can say. And with this primary aim, there were 5 parts of objectives that were defined. So these 5 objectives that were defined were basically, first of all, a basic research promotion. So a basic research promotion, mainly basically this was about the funding of the research, that whatever research is being carried out by the scientists or the students or the engineers, if it is interesting enough, it is important enough, the funding would be provided by the government of India. So government of India will help them in basic funding. They will also help them in creation of centers of excellence, so that the scientists could come together, collaborate in all these different fields. So those kind of setups were also built by the government of India to promote nanotechnology further. So that's why a basic research promotion was provided as a part of nano mission. Then after that we also see that, so that's why funding of basic research of by individual scientists or group of scientists, and creation of centers of excellence for pursuing the studies leading to fundamental understanding of matter that enables the control and manipulation at the nanoscale. The second was infrastructure development. Now, infrastructure, especially when it comes to technologies like nanotechnology, is very, very crucial, mainly because of the fact that the infrastructure is costly. Infrastructure is costly. That, for example, let's say something as simple as getting atomic force microscope or scanning tunneling microscope can be very costly. Can cost, a good microscope would cost you in the range of 8 to 10 lakh rupees. So that's why it's not possible for an individual student or an individual scientist to start spending this much. They would need the backing and the support, the financial support of the government. So this was provided, that infrastructure support wherever they needed it, this was also provided. At the same time, the kinds of facilities that were required, the equipments that were required, all these things were given. Even let's say the intellectual property rights, wherever this is required, that also was being held by the government. So that's why in all these cases, wherever there was a financial constraint for an individual or a group of scientists, we see that this is where the government of India also came forward in helping all these scientists and engineers in this field. Then apart from that, nanotechnology, nano applications and technology development programs. Now in this particular case, this was a very, very important point in this nano mission, that this basically talks about that how whatever research and development happens in this field, it should happen in a manner that it also helps, not only, this is not only about basic research, but the research is happening according to the needs of the country, according to the needs of the industries. That if the industry has a certain requirement and it comes to the scientists and engineers to provide a solution, they should be ready to do that. So that's why it should not be just a rampant research that you do or a blind study that you keep doing, but rather it should be focused. It should be focused upon the requirements. It should be focused upon the needs of the country or needs of the industry. So that's why we see that to catalyze the applications and technology leading to products and devices, the mission proposes to promote application oriented research and development projects. And that's why special efforts to be made to involve the industrial sector into nanotechnology research and development directly or through public private partnerships as well. So that's why overall this is something that was very, very unique point of this umbrella scheme, that it was mentioned in the objectives itself that whatever you work upon, try to have the context in place so that you know what end or what target you are working for. So that's why this also became a very, very important point. Then after that, human resource development. Human resource development also becomes very, very crucial to provide effective education and effective training to all the professionals and all the researchers who are in various different fields, so that they can understand the interdisciplinary nature of nanotechnology. Because understand this, that when it comes to nanotechnology, it is not an independent science. Space technology is an independent science. Nuclear technology is an independent science. Biotechnology is in an independent science. But nanotechnology is an application based science. That nanotechnology will be applied in space technology, nanotechnology will be applied in biotechnology, nanotechnology will be applied in energy sector. So that's why it's an application based science. So better research, better training, better education is required for the people who are working in these particular fields. So that's why human resource development is required. Not only that, even from the perspective of law, even from the perspective of law, we need people who understand the IPRs, who understand nanotechnology. That tomorrow, if the innovations are happening in India and are being done by the Indian scientists, then there should be a legal backing system also that can help them in terms of if there is any international controversy, or if they are stuck with some kind of IPR battle with somebody, then in that case, there should be a mechanism to help out these scientists and these, let's say, Indian companies. So that's why there should be somebody who is trained enough in understanding the IPR laws related to these innovations, and they should have a fair knowledge of what nanotechnology can be. So that's why that kind of human resource development was also required and also was taken as a part of this mission. And then finally, the international collaborations. That international collaborations regarding that how Indian scientists would work and how they would collaborate with the international scientists, that how some projects can be taken where Indian scientists and some scientists from some country are working together. Even the seminars that were held internationally, Indian scientists were sent to these seminars so that they can go there. Some kind of knowledge sharing will happen. They would understand things better. They would explain things better. And all these ways, they would be able to grow better in the field of nanotechnology. So that's why these five primary objectives were taken as a part of the nano mission. And this really helped in ensuring that we understand how to use nanotechnology. And then we saw that better applications of nanotechnology happens. All the scientific setup that we have in India, they also start working. For example, organizations are CSIR, like CSIR, are playing major role in nanotechnology applications and research in today's world. So there are all these developments that could happen because of the initial support that was provided by this nano mission. So that's why nano missions becomes a very has played a very crucial role altogether in this entire setup. Now, looking at some of the challenges that we have faced when it comes to innovations in India. So, what are the challenges and what are the possible solutions? What are we supposed to do? So, first and foremost, we need improvement in efficiency, reliability, and the safety of the products. So we need to understand that whatever we are doing, whatever we are innovating, it cannot be of substandard quality. It cannot be inefficient, because when you are entering the market, you have to enter the market with and while gaining all the faith of the market also. So you have to ensure that all these things are also in place. So that's why until all these things happen, you cannot really get the faith of the market and establish yourself in the market. So that's why these innovations have to be reliable, have to be efficient. Then one problem has been the cost of acquisition. As we discussed, that intellectual property rights can be, or nanotechnology infrastructure can be very costly. So that's why it's not so easy that you can get the access to all this infrastructure and the IPRs easily, because the government will have to pay a lot in acquiring each and every IPR or buying each and every instrument or equipment. So that also becomes one of the hindrances, one of the challenges. Then safety, health, and environmental risks to consumer and the public need to be addressed while commercializing nanotechnology. This is very true, and we'll also discuss about some basic problems that we have seen in the next slide as well. But it becomes very crucial, because if nanotechnology or nanomaterials are being used, what can be the cons of nanotechnology, what can be the drawbacks of these nanomaterial. We need to understand all these things as well at the same time. So that's why we need to address all these issues as well, so that people are not kept in the dark. They know the goods and the bads of what nanotechnology is. Then poor lab firm integration. Now, the meaning of lab firm integration is that the coordination between the research and the industry is not that great. All right. Poor coordination between research, or rather academics, let's say academics, and industries. Meaning that we see that many a times these studies that are happening, the researches that are happening are quite independent in nature. They are not really collaborating with the industries. What was mentioned as one of the key objectives is not really happening here. So that also becomes one of the challenges, and we need to address these challenges so that according to the requirements, these things are being done. And this is where we have seen that the lab form integration, if you take artificial intelligence as an example, artificial intelligence is an example where lab form integration has been wonderful, because we have seen that everything that artificial intelligence is doing today is actually helping the industries, or rather is catering to the needs of the industries. So that's why there is such a quick growth that we have seen in terms of artificial intelligence. So that's why the same somewhere also needs to happen with nanotechnology as well. The interdisciplinary nature of nanotechnology and the scope of its application is also one of the biggest challenges that we discussed about this, that it is pretty much an application based science. So then in that case, becomes very very difficult for an individual scientist to even work on various fields unless they are good, or they have a good expertise in at least two of the branches, one being nanotechnology and one being something else. They cannot contribute as much as you would want them to. So that also is one of the key challenges that we really have to think upon. Then the regulatory capacity, information asymmetry, and the lack of interagency coordination. This also becomes one of the key challenges in India, that there are various organizations, there are different ministries, there are different government bodies, they are all working in the same field. So whether for any project there is a coordination, sometimes no, sometimes we see that there is no proper coordination between them. So that also becomes one of the hindrances in any kind of application. Let me just give you an example, that there are some projects related to nanotechnology that are taken by the Ministry of Science and Technology. All right, some of these are launched by Ministry of Science and Technology, and there are some other programs that are being run by the Ministry of IT and Electronics. So on one hand, you have Ministry of IT and Electronics. On one hand, you have the Ministry of Science and Technology. They are working on some projects independently, and they are working on some projects independently. Whether there is a coordination between the two, sometimes not. So that is where the problem lies. That there has to be a coordination between all these agencies and the government bodies so that they can take a step accordingly. All right, they can take a step accordingly. So that's why it becomes really really important that all these things be uh, visible for to us as well. Lastly, when we look at the various concerns that we have about nanotechnology, first thing about nano pollution. Now nano pollution, when we look at it, first and foremost it will be hazardous to human health. Now when we are talking about nano pollution, there are two problems that there are 3 points basically, we can say that these are connected points. So when we look at these points, first is nano pollution, second is buckyballs. It is not bulky, it is buckyballs, the fullerenes that we had discussed. So the fullerenes have been found in fish, and environmental issues, they can cause lung problems. Why? Because these nanoparticles are very, very small, right? They're very, very small, and you can very easily inhale them. They can very easily enter inside your body without you noticing. And they can just keep getting deposited inside the body for a very long time without us realizing that they are just depositing. Maybe they'll start causing issues 10 years later, 15 years later, when a lot of deposit has happened in the lungs or maybe other parts of the body. So that is the problem, and that is the danger of nanotechnology or nano pollution for that matter. So that's why we need to understand all these concerns as well, and the problems that it can cause. You might have heard of microplastics. Microplastics. So when we look at microplastics, microplastics are what? These are very tiny plastic particles. And today we see that microplastic pollution has been increasing a lot. We have found it in the samples of water everywhere. Sea water, ocean water, lake water bodies, everywhere we have found the samples. In the air, we have seen that microplastics are there. In the bottled water, there was a research that was conducted a couple of years back. In the bottled water, they found that there were samples of, there were trace particles of of microplastics in the biggest of the brands of packaged drinking water. So that's why we have seen that there are all these cases of nano pollution, and they can keep on increasing in the coming days. So for example, let's say when buckyballs are found in fish, there are two aspects you have to understand from the environmental perspective. One, that something that is called as bioaccumulation, and secondly biomagnification. Bioaccumulation and biomagnification. So bioaccumulation is what? Bioaccumulation is when in a given species we see that something kind of a pollutant keeps on increasing in its concentration. So that is called as bioaccumulation. Horizontally along among a species, among a trophic level of the species, we see that this increases. And when from one trophic level to another, we know that there is a food chain, that smaller beings will be eaten by the bigger beings and will be eaten by the biggest beings. So in that case, biomagnification happens. So the concentration will keep on increasing from one trophic level to another. So that's why this will cause major trouble to the ones that are there in the third or the fourth trophic levels. So it can become a very dangerous trend. So that's why we have to understand this in the context. Nano pollution, the lung problems, the buckyballs that have been found, how all these can be very, very dangerous altogether. Then titanium dioxide in sunscreen. Now, this was again a very peculiar case, because initially all the advertisements of sunscreens would tell you or would advertise you about titanium dioxide. That they would show you the advertisements where the sun rays are just reaching your skin and they are just reflecting back off your skin without entering your skin, because you are using titanium dioxide in your sunscreen. So all looked very good until a research was conducted on the poor mice, where they found that over a certain limit, if the concentration of titanium dioxide is very high, it can in long term lead to skin cancer. It can lead to skin cancer, that titanium dioxide particles can get deposited under the skin and they can reside there for a very long time. This was found, and then there was a restriction put that not more than, I think, 10 nanogram per centimeter cube. I think this was the target, the limit that they had kept, that you can't use more than 10 nanograms per centimeter cube of titanium dioxide. So what happened initially? Everyone kept using titanium dioxide in beyond certain limits, and then the restriction came. So that's why these kind of misses are could be there, and this can be a very dangerous trend altogether. So that's why this is also something that we need to consider. Then cadmium selenide poisoning, calcium selenide nanoparticles leading to cadmium poisoning. So cadmium selenide basically you would find in quantum dots. Quantum dots. So this can actually lead to cadmium poisoning. Now, many of these cases, when we talk about metal oxide metal oxide nanoparticles especially can be dangerous, because they could be made of some of these elements, some of these metals uh, that are poisonous. So that's why they can be dangerous for the health. Then lack of risk analysis and regulations. This is also one of the problems, that when you look at the regulations that we have in India, these regulations only have been introduced in terms of nanotechnology in the last 3-4 years only. Before that, the whole nano mission, when it was running, there were no limits, there were no limitations or regulations that were put by the government, because they also wanted that let them do something, do some research, and later on, when time is right, we perhaps will also introduce some regulations. Because in many cases, when regulations or laws etc are introduced in the early part of the development of technology, many times we see that nobody will be interested, because they know that there are so many rules and there are so many regulations that I have to adhere by. Better let's skip it and not even be in this research field. So many a times what the governments all across the world, they do it, that they don't put any regulations or laws or checks and balances in all these cases, and they'll just let the technology prosper, and then later on they do that. So that can become dangerous because you don't know whether it will be used for negative purposes. Many a times that is also a possibility. And then lastly, there is this concept of grey goo, which is nothing but the concept of nano robotic army. The concept of nano robotic army. So overall, it's a possibility. We know that today we can create nano machines. So what stops us from making nano robots in and recruit them in armies in tomorrow's world? So that's why there are all these concerns that we have about nanotechnology. So although when it comes to the application areas, we do understand that there are immense possibilities where we can make the use of nanotechnology, but at the same time we also need to check our steps in certain cases, and we need to understand some of the key problems that we might face, so that we keep on addressing them from time to time and not let that explode. So that's why we need to keep a check on the various concerns without around nanotechnology. Look at this question. This was asked in your paper. I'm launching the poll for you. I'll give you 1 minute time. Please mark your answers. All right. So as I see, 58% of you have marked the correct answer, that is D. But then there are some of you who do not believe in this answer. So let me read the question for you. There is some concern regarding nanoparticles of some chemical elements that are used by the industry in the manufacturing of various products. Why? First, they can accumulate in the environment and contaminate water and soil. Correct? We discussed about bioaccumulation that can happen. So yes, they can contaminate water and soil, and also even air they can contaminate. So yes, they can enter the food chain. We discussed about this. That is what biomagnification is. So this is also correct. This is also possible. They can trigger the production of free radicals. Is this correct? Even this is correct. This is what happens with titanium dioxide, that it leads to the production of free radicals. Now these free radicals basically are charged particles. In a manner, you can say that these are charged ions which are not good for us, and we need antioxidants. I'm sure you have heard of antioxidants. We need antioxidants to control the free radicals. So that's why we see that yes, it also is possible. So correct answer will be 1, 2, and 3. Look at the next question, the last question. Please read the question. Meanwhile, I am launching the poll also for you. This question was asked last year in 2022 paper. This question was asked. I see that many of you have also asked questions. After this question, I'll take your after this question, I'll take your questions or your doubts here. Hmm. Wonderful. 83% of you have marked the correct answer. That's great to see. So, consider the following statements. First, other than those made by humans, nanoparticles do not exist in nature. First of all, do not is an extreme word, but they do exist in nature. The first nanoparticle was discovered, right? Fullerenes were discovered, graphene was discovered. So, they occur naturally. That's why they were discovered. So, this is wrong. Nanoparticles of some metallic oxides are used in the manufacturing of some cosmetics. We discussed about sunscreen and titanium dioxide there. So, yes, correct. Nanoparticles of some commercial products while which enter the environment are unsafe for humans. That's also correct. We discussed about the nano pollution problem. So 2 and 3 both are correct. All right. So this brings us to the end of this particular chapter. Now, I do not wish to start the next chapter because the next chapter that we have is robotics and artificial intelligence, which is almost a 2 hour chapter. I don't want to let it hang in the balance. It's better that we start fresh next Saturday and we complete this entire part. So, meanwhile, if you have any questions with regards to whatever we have discussed in the last 1.5 hours or so, please let me know. We'll have a discussion on that, and then after that, we'll end the session. Nanowires again please. So nanowires basically would be very small wire. Nano because the diameter of the nanowire will be just 1 nanometer, in the range of 1 nanometer. That's why they are called as nanowires. They will be made of semiconductor material most of the times, and sometimes metallic material also. And they would be very helpful because they have very good magnetic and optical properties, and that's why in electronics, in circuitry, in electricals, they would be very useful. And even in the storage, they will be immensely helpful, so they can increase the efficiency of computer storage. So that's why they are very useful. What is nanoflares? Nanoflare is something that we use in the treatment of breast cancer, and this helps us in mapping of the problems or the cancerous cells that might have occurred because of cancer. So that is where we see that quantum dots are actually used. Rotation won't shake the alignment. It's a yeah, I understand where you're coming from. That's why it becomes a very difficult project to implement, because there has to be an alignment, and whatever rotation period the earth has, your space station etc should also have a similar rotation, so that you can create a stability between these 2 points, which is not going to be easy when it comes to the low earth orbit. So there are multiple such factors. When you look at the technical document, there are multiple things that they actually have written there. Please explain again quantum dots. So quantum dots basically is nothing but the case where we see that uh, we have very small particles. We have spherical particles made of semiconductor material, cadmium selenide to be exact, and we see that they can actually be used in various ways, because when ultraviolet light falls on these quantum dots, they emit various colors, and these colors that they emit, it depends on the size of the quantum dot. So then in that case, we see that photovoltaic devices, electronic devices, medical devices etc, they can all make the use of quantum dots. Is Iron Man mask possible to build based on nanotechnology? The suit that Iron Man uses, basically he uses nanotechnology. If you watch the films, they mention nanotechnology multiple number of times, very frankly. What are antigens? Antigens, just wait. Next week when we discuss vaccines, we'll discuss about antigens properly. What is a biochemical sensor? So biochemical sensors basically are biological sensors which can be used in various ways. For example, they can be used in detection of some kind of problem, detection of pollution maybe. So in all these cases, these sensors can be utilized. So especially in the space technology, we see that these sensors, they have a very important role to play. Buckyballs in fish, can you explain? So buckyballs basically are nothing but the fullerenes. Now these fullerenes are nanoparticles. So these are very, very small particles. So these small particles have been found in the fish, deposited in the body, the lungs of the fish, meaning that they are consuming it from where? Maybe water bodies, correct? So that is a dangerous trend, because now these fish will be consumed by somebody, maybe some other animal, maybe by the humans. Then in that case, what happens? This bioaccumulation starts, that the same nanoparticle might also enter the body of the other organisms that are consuming this fish. So overall, this can lead to a very dangerous scenario altogether. Any other question? Anyone? Madame Curie and Pierre Curie, they got Nobel Prize 3 times. That's perfectly correct. Yes, and even later, their daughter also got the Nobel Prize. All right. So I think I have taken all the questions that you had. So let us end the session here. Next Saturday, when we come back, we'll start with robotics, right? So robotics and artificial intelligence will be our first chapter. Then after that, there are some other important chapters that will keep going on. So for example, diseases, defense, vaccines, intellectual property rights, IT and communication. All these are the various different chapters that we will discuss. At the same time, what we will also discuss are some of the mains based questions that have come from these areas of biotechnology and nanotechnology. So these are the things, and even energy. So these are the things that we'll discuss in the next class when we come back on next Saturday. Meanwhile, when you go back, please go back, revise everything, whatever we discussed in this weekend. If you have any questions, you can also write to me at rasesh.kumar@byju's.com. All right, so you can drop in your emails here if you want any help, if you want, if you have any doubts while studying, if you come across, you are always welcome to contact me here. All right, so this brings us to the end of the session today. Please go back, revise well, and let's meet back on the next Saturday. Thank you very much.